This is all joint work with Zoltan Füredi, some stuff we've done recently. Okay, so here is our motivation, and it actually is some problem for matrices. And so originally this was, I believe, introduced by Anstey and Shali. So we have some matrix M, and we say it's simple if it's a 0-1 matrix, so all of its entries are either 0 or 1, and it has no repeated columns. Okay, and so if we have a simple matrix M and just any other 0-1 matrix F, we say F is a configuration of M if M contains a submatrix, which is some row and column permutation of F. So essentially it just contains a copy of F inside of it as a submatrix. So in usual extremal combinatorics fashion, what we want to do is maximize some quantity given some constraint. So here we want to maximize the number of columns in our host matrix M such that we only look amongst all matrices that don't contain F as a configuration. Okay. So here's an example, a famous example. So let's fix some k, an integer, and let's F be simple matrix where basically we have every 0-1 vector of k as one of the columns. So here's the example where k is equal to 3, and we have 2 to the 3 columns here. And so what Sauer and Sheila proved is that so if M is a simple matrix, we have some fixed number of rows n, and we have more than this n 0 plus n choose 1 up to n choose k minus 1 columns, then we contain F as a configuration. Okay, but maybe this is more popularly formulated in another way. So in the language of shattering sets or VC dimension, so what does it mean to shatter? So I have some set family, so F, which consists of sets S1 up to possibly infinitely many sets, and a set T. So we say that the set family F shatters T if, so we take the intersection of T with all of the sets in F. So what do we get? What we should get is every possible subset of T, including the empty set and the whole set. Right, so that's why we have here the number of sets is 2 to the cardinality of T. And so what they actually proved was that if F is a set family on some ground set, let's say integers up to n, and we have more than this number of sets in our family, then we shatter a set of size k. And so if we look at this matrix here, basically we have every subset of 1, 1, 1 here. Okay. So another example, which maybe we're more familiar with, is sort of this Turán problem in graphs. So if I have some graph f, we define this function xnf. This is the Turán number of f. This is the maximum number of edges in a graph with n vertices, which is f-free, where here f-free means we do not contain a subgraph isomorphic to f. Okay, so there's many ways to view a matrix, or sorry, a graph as a matrix. Here we're going to look at the incidence matrix, graph F, or graph G. So from any graph, we have this matrix, which is 0-1 matrix, and each column contains exactly 2 ones. So in other words, here I have that the ijth entry of our matrix is going to be 1 if and only if our ith vertex is contained as an endpoint of the jth edge. Okay, and this is just kind of unraveling the definition of all this stuff. So if M is the incidence matrix of some graph F, sorry, some graph G, we fix some other graph F, and then if we contain more than the Turán number of F columns in M, then what we're going to find is the incidence matrix of F is some submatrix of M. And all that's basically saying is, well, the incidence matrix of F is a configuration of M if and only if F is a subgraph of G. So this is just another way of formulating the usual Turán problem but in terms of matrices. Okay, so our goal for today is to look at an R-uniform log. So instead of our host graph having exactly 2 1s in every column, we take a matrix where we have exactly R 1s, and we want to see what it means to forbid the incidence matrix of some graph. Okay, so before that, we will detour a little bit. So I know there were some talks about this previously, about Berge cycles and Berge copies of other graphs. So here's a picture of Claude Berge and Paul Erdős. And so there are many different notions of cycles and hypergraphs. And one of the first ones was introduced by Berge. So we call them today Berge cycles. And then from the Berge cycles, we generalized to many different things. So, okay, so first of all, what is a cycle in a graph? We have sequence of vertices and sequence of edges. So we have this V1, E1 up to VL, EL, and then we loop back to V1. With the property that the ith edge is just VI and VI plus 1. So here, when we mention the edges, they're really just redundant because each edge contains exactly 2 vertices. But when we work in hypergraphs, so our edges are allowed to have more than 2 vertices if we want them to. Then we get this generalization. Berge cycle, still we have some sequence of vertices and edges that loop back on each other. And the property now, we want this ith edge contains Vi and Vi plus 1. And maybe some other vertices, but we don't care about those. Okay, so this is what a Berge cycle is. And now I want to generalize this notion of cycles to other graphs. So let's fix any graph F, and we want to build what's called a Berge F. So we say a hypergraph is a Berge F if we have some way, so a way to map the edges of F to the edges of the hypergraph, such that if I have some edge xy in my graph, then whatever hyperedge I map it to, f of xy, it contains these 2 vertices, x and y. Okay, so here's, in my example, this is a C4 in a graph. This is a Berge C4 and another Berge C4. Okay, where this first one, this is a loose 4 cycle. It has this nice intersection structure between consecutive edges. Here we don't have nice intersections, but it still satisfies our definition. So if I have some graph F, the Berge Fs are actually a family of hypergraphs, not a single hypergraph. Okay, so for example, if I have a hypergraph H and it contains a set of vertices S, so I'll draw it here. So I have my vertices S, such that they have codegree K. So codegree of a set means the number of edges that contain this entire set. So here I have some K edges containing this set here. Then I want to show that I can find a Berge copy of any graph with at most size of S vertices and at most K edges. And how do we do that? So let's just draw a picture of S inside here. Okay, maybe something like this. Okay, so here I put down my vertices, and now all I have to do to satisfy this definition is, for each edge here, I map it to a distinct hyperedge, which contain these 2 vertices. But because we have at most K edges here, and we have K hyperedges that contain all of these vertices, we just can do it greedily. Okay, any questions about that? Okay. So now let's go back to this matrix stuff, and we're going to define something called induced Berge graphs. So,
can I go back?
Yeah.
So when you define Berge F, you want the for non-edges of F, do you want based on intersect or it's just pure?
It doesn't matter. Yeah. Uh-huh. Okay, so if we think back to the matrices, and so I have some R uniform hypergraph, which means that every edge contains R vertices. So this matrix is going to have exactly R1s in every column, zeros everywhere else. Okay, so what does it mean if I contain the incidence matrix of some graph F as a configuration? So here I drew, well, this is the incidence matrix of C4. So what does that look like within the hypergraph? So I have some 4 vertices, and my first edge, which is represented by the first column, contains the first 2 vertices, so maybe these 2. And it contains some other vertices. We don't know what they are, but we know that they're not any of these other 4 vertices. Okay, now my second edge contains the second and third vertices. So these 2, and then maybe they intersect out here, who knows, and then so on. Okay. So all we know is that when we look at exactly these vertices and then restrict to them, what we get is actually just a copy of the C4 in this case, which is the graph F here. Right, so if we read this, we get some set of vertices, some set of edges, such that the induced hypergraph, so we look at only these vertices, shrink down the edges to only these vertices. What we get is something that is isomorphic to the graph F. Okay, so this is what we're going to call an induced Berge F when we have this structure. And it's a little bit misleading because this induced Berge F is not the same sense of induced like subgraph in a regular graph. So what we mean is it's induced in terms of the matrix. Okay, right, so here I'll formalize it. This is again just the definition of Berge F, which we just discussed. And here's the definition of induced Berge F. So again, we want some way to map the edges of F into the edges of our hypergraph, but instead of just having my vertices xy being contained in f of xy, we want this exact condition where the only vertices that f of xy contains within these representative vertices are x and y. Okay. So just to drive the point home, so suppose I have some 3 vertices and they're contained in hyperedges like this, so 3 different hyperedges. So here I can find a Berge triangle, but it is not induced. Because all of these hyperedges contain exactly these 3 vertices. Okay, any questions about definition? Okay, right, so just for ease of writing this, we're going to let BF denote the family of all Berge Fs, this end BF to be the induced Berge Fs for some given F. And define this Turán function for our uniform hypergraphs. So right, this R is always going to denote the uniformity of the graphs that we're looking at. N is the vertices, so here we look at the maximum number of edges in an R uniform in vertex F-free hypergraph. Or F is some family of hypergraphs. Okay, so our goal is to understand the growth of these 2 functions. So when we forbid the Berge Fs and the induced Berge Fs. And for all of our results, F is going to be some fixed graph. N is going to be arbitrarily large, so does not depend on F. And then we're going to look at the order as R, the uniformity grows. Okay, so here are some sample results of this nature. So first is the Turán number of even cycles. So if we forbid containing some even cycle of length 2k, maximum number of edges we can have is big O of n to the 1 plus 1 over k. And so this is still open to determine if this is the correct order, i.e. to find a matching lower bound, or maybe show that this is not best possible. Okay, but when we move to the Berge setting, so Dury and Lemons prove that as soon as R is greater than or equal to 3, the uniformity, then, so if I want to forbid a Berge cycle of length 2k, again I get the same bound, n to the 1 plus 1 over k, that's my upper bound. But more interestingly, I can also forbid 2k plus 1 cycle, so an odd cycle, and my upper bound is also this n to the 1 plus 1 over k. So this is interesting because here's where it starts to differ from the graph case. So in a graph, I have very dense graphs that forbid odd cycles. Namely, I can take a complete bipartite graph. This has n squared over 4 edges, where this n squared is much bigger than this n to the 1 plus 1 over k. So the idea is, as we grow our hyperedges, say we allow more vertices in the edges, it becomes easier and easier to find these Berge copies of graphs. Right, so we also have this nice fact that if we just care about the order of growth of these functions and not, constants or coefficients or whatever, then eventually this is going to be a non-increasing function. Okay, maybe I'll skip the proof for that, but it's quite simple. Oh, does anyone have any questions so far?
But the non-increasing, but the equation is like, you use big O notation?
By non-increasing, I mean non-increasing in the order of growth. Yeah, so maybe the constants get bigger, but the total order does not. Yeah. Thanks. Okay. So here are a couple of tools that these arguments use generally. So if I have some R uniform hypergraph H, I'm going to define the two shadow of H to be a graph on the same vertices, where I put the edge x, y, if and only if the pair x and y are contained together in some hyperedge of H. This is called my two shadow. So in particular, if we have some hyperedge, it has R vertices. When I look at the shadow, what I get there is a clique on those R vertices. Okay? So we have this property that if H contains a Berge F, and the shadow will also be able to find a copy of this graph F. But the converse is not true in general. So here is an example. This first thing is a Berge C4. And when I take the shadow, I turn all of the edges into 4 cliques. And here I can find very long cycle. But in my hypergraph, the longest Berge cycle has length 4. Okay? And right, the problem here is I'm kind of reusing edges within the same hyperedge to get a long cycle. Okay, so now we introduce this new function, this x and krf. So this is called the Generalized Turán function, and this is a parameter in graphs. So this is the maximum number of cliques of order r in an n-vertex F-free graph. So we call it the Generalized Turán number because in the case where r is equal to 2, we're just counting the number of K2s in an F-free graph. That's just the number of edges. So in that case, this function is equal to the regular Turán number. Okay. And there's a number of results here. So for instance, this first result by Erdős and Zykov. So they proved that if I forbid some big clique of order KT, and I want to count the number of smaller cliques of order R, then the graph that maximizes that is exactly this Turán graph. And then, so also during limits, they didn't actually prove this result for cycles, but it can be seen as a corollary of their hypergraph result. So they showed that the maximum number of cliques of order R in a graph which forbids C2k or C2k plus 1 is, again, this big O of n to the 1 plus 1 over k. And then the last result is by Alan and Schickelmann, who they really popularized the study of this function. They showed this result for forbidding complete bipartite graphs. Okay. So what we want is a way to relate all of these functions that we've been talking about. And so there's this really nice lemma by Gerbner and Palmer, which says I can bound this Berge F Turán number for our uniform hypergraphs. So on one side here, I get this generalized Turán number for the lower bound. And for the upper bound, I have, again, this generalized Turán number plus the regular Turán number. Okay? N? Oh, sorry. This M here, right? You mean? I think there should be N. I'm not sure. Sorry. I changed some of, oh, no, I think it should be R. Sorry. Yeah, I'll check it later, but I changed some variables so it would be the same as everything, but then I forgot to change that. Okay. Right, so here, this allows us to instead of working in hypergraphs, we can consider problems in graphs instead. So maybe here it's a little bit easier. We have some more theorems and lemmas to work with to help us. Okay. And yeah.
This doesn't depend on S or T.
So we have T should be at least like S factorial. I it's in here.
Oh,
okay. Yeah. Okay. Okay. So in the case where R, so R is the size of the cliques or the uniformity, is greater than or equal to the number of vertices in the graph we're forbidding. So what is this function? Maximum number of R cliques in an F-free graph. Well, as soon as I have a clique of order R, then I have a copy of any graph on at most R vertices. So this function should be 0. And so if I plug in 0 here on the right-hand side for this upper bound, so I have now that this Berge Turán number is at most 0 plus the regular Turán number, which is always at most n squared. Okay, so eventually these numbers are all, if we only care about the order, they're all dipping below n squared. Okay, right, so this is a result by Gross and Tompkins. So for every F, there exists some threshold R naught. So this is the threshold for the uniformity, such that if we look at hypergraphs, where the uniformity is bigger than this threshold, then now this Berge Turán number is actually little o of n squared. Okay. Okay. And all right. So just a couple more facts. So in the case where so we're still forbidding some graph F, and we're counting the maximum number of KRs in an F-free graph. So in the case where R is at most the chromatic number of F minus 1, well, what we can do is just take the Turán graph. This contains no copy of F, and it has of the order n to the R cliques of order R. And really this is like the maximum order that we can get. So what that says is this Berge Turán number is of the order n to the R. Okay. So here I have a graph here that I drew. So what we're going to do, we fix some graph F. For simplicity, let's suppose that F is not bipartite. And we want to look at the order of growth of this Turán number of the Berge F as R goes to, or as R grows. So say it's of the order n to the alpha, where alpha depends on R. And here we can track what alpha is going to look like. So in this first portion where we have this straight line, this is just because of this first or second bullet point here, that we can increase in order until we get to chromatic number -1. Here we have no clue what happens, and then eventually we hit our threshold thing and it dips below n squared. Okay. Right, but really, in between in general, we don't know. Okay, we don't even know maybe if it's increasing, decreasing, or anything like that. Okay, so now let's talk again about these induced Berge Fs. So we have this chain of inequalities. The first two was what we displayed earlier, that this maximum number of cliques is at most this Turán number for Berge Fs. And then we also have that that is less than or equal to the Turán number of induced Berge F. So why is that the case? If I have some hypergraph without a copy of Berge F, then it also does not have a copy of an induced Berge F. Okay? Okay, so for any graph F, which is not equal to the star for some value of t, so k1t, we actually get that the order of growth of this function of this induced Berge F is non-decreasing, right? So the regular Berge F1, it was non-increasing eventually, and now this one is non-decreasing. So let's see why that's true. I'll draw it here. Okay, so I'm going to start with some hypergraph H, which is a n-1 vertex r-1 uniform hypergraph with the extremal number of edges and no copy of Berge F, induced Berge F. Sorry, this should be IB of F. Okay, and then I create a new hypergraph H prime by adding a new vertex, let's call it V, and then just inserting it into all existing hyperedges. Okay, so we do this for all hyperedges of H, and this gives us some H prime. Okay, so the observation here is that if H was induced Berge F free, then also H prime should be. So why? Suppose it does have an induced Berge F, it must contain this new vertex as one of the representative vertices, but this new vertex is contained in every edge. And the only graph which has some vertex contained in every edge is the star. So this k1t for some t. So that's a contradiction. Okay, so then we get this nice inequality that the number of edges here is at least the number of edges here. Okay. And so also what does that say? So again, I note here that this induced Berge F function is bigger than this maximum number of cliques in an F-free graph. So I have that this function here, so I forbid induced Berge F, this is at least of the order of all of these functions. So when I forbid F and then count the number of ks for any s greater than or equal to r. So this uses two things. It uses this inequality here, and it uses this sort of stepping up inequality for every r. Okay, any questions about that? Okay. So again, the corollary is just exactly what I wrote before. So if it's bigger than, or at least the order of every one of these generalized Turán functions, then in particular, it's at least the order of the maximum value. And so what we proved was, actually, this is the correct order. That if so for every graph, which is not exactly just the star, the Turán number of the induced Berge F is of the same order of wherever this generalized Turán function maximizes. Okay, so in other words, all we have to do is show an upper bound because we already got the lower bound above. Okay, so I would like to show some of the proof idea. And so largely we use these notion of delta systems or sunflowers, and we find something called a core of the hypergraph. So fix some natural number alpha, and we say some subhypergraph A of H is an alpha core of H if for every subset S on R minus 1 vertices, either these vertices have very large codegree, at least alpha, or they're not contained in any edge of A at all. Okay, so I'll just draw a picture here. Again, we have the set S of R minus 1 vertices. And in my core, so the codegree of these vertices is at least alpha. But all of my edges have size R. So that means here's R minus 1 vertices. I have one additional one in each edge. And we have at least alpha of these. Okay, so in other words, for every R minus 1 set, we can view it as a core of a sunflower with at least alpha petals. Either that or they're not contained in any hyperedge at all. Okay, and so in general, we have these alpha cores. For example, I can take a hypergraph, and then its alpha core could be the empty set or the empty graph. So this satisfies it trivially. But what we would like to do is find some large alpha core within our hypergraph. Okay, so here's why we use this alpha core thing. So we have this lemma. So if alpha is large, at least the number of vertices, minus 1, and we have some non-empty alpha core. If we look at the 2 shadow of the alpha core, A, then this contains a copy of F if and only if the alpha core contains an induced Berge F. Okay, so let's look at a proof. Okay, and I'll draw along with it. So we look at the 2 shadow, so we reduce from this hypergraph to the 2 shadow, which is a graph, and suppose we have a copy of F. Okay, so as a subgraph, yeah. Okay, so maybe here's F. Okay, so by definition, each pair of these vertices, which are connected by an edge in the shadow, are contained in at least one edge together in alpha, or sorry, in A. So what I can do is I can pick an edge, a hyperedge containing each of these edges. Okay, so I want to choose it in a way that basically the number of conflicts that I get is minimized. So I look at all of the edges I choose, intersect it with the vertices here, and the summation of that, I want that to be minimized. Okay, so in the case where we can successfully map each of these edges to a hyperedge, such that the hyperedge contains only exactly those 2 vertices, we get our induced Berge F, and we're done. So the bad case is if maybe we pick some edge which contains, say, x and y, and our edge that we pick also contains some other vertex here. So this is EXY, but also, unfortunately, we get this vertex C in there. Okay, so what do we do there? So now we want to use the property of the alpha core. Okay, so okay, this is exactly what I said. Let's look at this edge, E of xy. So here's x, here's y, and we have this bad vertex Z in here. So I want to pick some R minus 1 subset of this edge. And the one I'm going to pick is just everything except this Z. So this is going to act as my set S in the definition. So I know that this set is contained in many different edges. So I get something like this, where basically I'm replacing Z with new vertices. And if I have enough of them, I can choose one of these edges such that the last vertex is not contained in this vertex set here, F. And so now I decrease the number of conflicts. Okay, and I keep doing this until I get exactly what I want, which is an induced Berge F. Okay, any questions? Okay. All right, so now let's show that we actually have one of these alpha cores, which hopefully should be non-empty. So here I'm going to look at in vertex R uniform, and I add this extra condition for R part type hypergraphs. We'll deal with the non-R part type case later. So we can partition our vertex set into R parts, say roughly of equal size. So V1, V2, and so on, such that each hyperedge contains one vertex from each of them. Okay? And what I'm going to do is here's V1, in general Vi. Okay, so if I have the hyperedge H, I define this H of I to be, I just delete the I set, and then every hyperedge is shrunk down to an R-1 set. Okay, so this is R-1 uniform. So our lemma, which shows the existence of an alpha core. So for every alpha, I can find an alpha core such that the number of hyperedges I delete in order to get to this alpha core is not too many. So namely, it's close to alpha minus 1 times the number of edges in each of these well, not technically sub-hypergraphs, but these R-1 uniform hypergraphs. And those are going to be useful later for induction because we're going to be inducting on R. Okay. Okay, so now we can start doing the actual proof. Okay, so we induct on R. In the case where R equals 2, so this induced Berge F is exactly just a regular F in our graph. And so this Turán number here is exactly the Turán number of graphs. So we get that. So now we look at R greater than 2. So first thing we do is we reduce to an R partite subhypergraph of our hypergraph without losing too many edges. So we still have some constant times the number of edges we started with. You could do like a probabilistic construction, for instance, for the subhypergraph. And then we find an alpha core of this new hypergraph H prime. So we used the lemma before, which says we can find this alpha core without deleting too many edges. In particular, the number of edges is at most the number of edges in the alpha core plus this weird thing here. Okay, and now we use this observation that in each of these R-1 uniform hypergraphs, we do not contain an induced Berge F. Because if we did, we would also we would have an induced Berge F in our original hypergraph. So we can apply induction to those because they're R-1 uniform. Okay, what else do we have? So in this alpha core, if you recall, its shadow does not contain any copy of F. Otherwise, we wouldn't contain an induced Berge F. So here, the number of edges and the core. Well, when I take the shadow, each of these edges gives me a clique of size R. So it's at most the number of KRs in the 2 shadow. And now this 2 shadow category, the number of KRs is exactly just this generalized Turán function. Okay. So putting it all together, now I just want to count the number of edges in this H prime. So here I replace the number of edges in A by this bound here. And then the rest here is by doing induction on this term over there. Okay, and then here I get this KR here, and then I have this KS for every S at most R-1. And that's exactly the bound that we wanted, at least of the correct order. Okay, so you can take a minute to digest it if you want. Okay, time's up, so we move on. So here now I graphed like the order of all 3 of these functions. So the red one again is this Turán number of the Berge F. The blue one is going to be the Turán number of the induced Berge F. And then this green line is for the generalized Turán number. Okay, so we talked about red already. For the green, so again, up until here, we can just take our construction to be the Turán graph, and then eventually we get to 0 because we have no more large cliques if we want to forbid a graph F. So what is interesting here is that none of these functions really act like each other, at least eventually. And this induced Berge F, we noted before that this is always non-decreasing in order. It maximizes somewhere, and then it just is constant. Okay, but in terms of like where does it maximize, this is still very open. Okay. Okay, so there were a couple of cases where we could do something slightly better. One of them is the case where we forbid induced Berge cycles. So a cycle of length L. So basically we repeat the same proof, and at some point we arrive to this alpha core of H. Okay, where alpha I'm just going to put as L, which is the size of the cycle. Okay, so suppose what we want to show is that we have no edges, hyperedges at all in this alpha core, or this L core. So suppose for contradiction that we do contain at least one hyperedge. So this is an edge of with R vertices inside of it. We look at the shadow, and in the shadow we have some KR. Okay? So in particular, this KR contains a cycle of any length up to R. So in the case where the cycle we're forbidding has length at most R, we already get this copy of the cycle, which means in the hypergraph we get this induced Berge copy of the cycle by the lemma that we showed. So what's left to consider is the case where we forbid cycles longer than R. Okay, so we actually have now this nice fact that if I do have some induced Berge cycle of length t, then I can actually upgrade it to an induced Berge cycle of length t plus 1. And I can keep doing this until I get all the way to induced Berge cycle of length L. So how do we do it? So here we have our induced Berge CT. We have some hyperedge here containing the representative vertices x and y. So we want to use the properties of the alpha core. So I'm going to take two different R-1 sets. The first set is going to be everything in this hyperedge except for the vertex y, and the other one will be everything except for the vertex x. So for the one that doesn't contain the vertex y, I can find some hyperedge, which basically is the same thing, and we replace y by some y prime. And if we have enough of these, then we pick y prime to be outside of the existing representative vertices. And then I do the same thing here, where I replace x with x prime. I pick some arbitrary intersection. And now what I have is I can replace this one hyperedge with two hyperedges and grow my cycle by length 1. Okay, so this is kind of a special property for cycles. It doesn't work necessarily in general for all graphs. Okay, so instead of getting this weird bound with the cliques and whatever, what I get here is that this induced Berge cycle Turán number is of the same order of growth as the regular Turán number of the cycle. And in particular, now if I know this function here, at least the order, then I also know the order of this generalized Turán function. So I forbid CL in a graph, count the number of KRs, and it's going to be big O of the Turán number of the cycle for all R at least 2. So in particular, this is a slight improvement of the Diori-Lemons upper bound that they got, at least for even cycles. For odd cycles, this is not sharp. Okay. Okay, just also because, so in all the proofs before, we forbid the case where f was equal to a star. So we decided maybe we should actually consider that. And so we get some actually better bounds where the coefficient is almost the same. You can ignore the first line. In the cases where we have some reasonable divisibility conditions on the number of vertices, we get upper bound and lower bound, which, so here we have this -3 and -2. And maybe the gap can be closed more. Okay. And then for the last few minutes, I'll just talk about some open problems and related questions. So mostly everything is open related to this. In particular, for all of these things, we really only cared about the order of the growth of these functions. So still, like, determining the coefficients and everything for, like, exact bounds is very open. So, right, determine more precise bounds for this function for basically any choice of f that you want. For instance, the triangle maybe is something fairly easy that can be done. Another direction, so if you can find some other way to calculate the order of growth of this induced Berge Turán number, then what that also gives us is some bounds for this generalized Turán function, this counting number of cliques in every graph. So a lot of people care about this type of problem, and mostly everything is open in the case where the size of the clique lies between the chromatic number and the number of vertices in our forbidden graph. And so that's what the last thing is. Okay. So for instance, there are still some open questions for this generalized Turán number. So I think Corey Palmer also presented this problem, but this is a problem which was posed by Erdős. So if we forbid, so this is like a blow up of K3, what's the maximum number of K3s that we can have? So basically, how many K3s force a large blow up of the K3? Okay. And so lastly, I also want to mention a related question. So something even more induced than what we're working in. So it's this notion of F expansions. So if I have a graph F, I want to have some sort of hypergraph version of this graph F. And so an expansion is basically for every one of these graph edges, I put in R minus 2 additional vertices, such that all of these vertices are distinct. So there's a unique R uniform F expansion. And so these problems are quite related, but this F expansions one seems to be, in general, much harder. And there are many questions that are still open to those. Okay, so thank you.